Hello, welcome to Zigmatech Learning Hub. I will be your instructor for physics. For this class, we are going to be taking our exercises from Examguide app. If you don't have the application already installed on your device, I will want you to download the app in order to follow along in this class. Examguide is a leading educational app that helps students prepare adequately for various exams like UTME, post-UTME, WAEC, JCE, KCPE, IJMB, JUPEB, KCPE, BECE, JSCE, NCEE, NECO, etc. You can download the app from www.examguide.com or Google Play Store. Please subscribe to our channel and turn on the notification bell and get updated on new videos. Are you ready for this class? Okay, let's get started. Welcome to physics class, and we are going to be learning simple harmonic motion. By the end of this lesson, you should be able to explain the energy of simple harmonic motion. That is energy of a simple harmonic motion of a simple pendulum. Then we look at the energy of a spring. We're also going to do in the second, we're going to explain period of a simple pendulum and period of a spring. Then 3 is to apply the relations of energy and period of simple harmonic motion to problem solving. If you are ready, let's get started. Now, when we talk about simple harmonic motion, we have done simple harmonic motion 1. The simple harmonic motion we are going to do now is, like we said, from the specific objective, is considering the energy and the period. Now, let's talk about the energy of this simple harmonic motion because it is a very important aspect. Now, the energy of a simple pendulum, when you are considering the motion on the screen, you realize something. The velocity is always reducing after some time. At a particular point, the velocity will be 0, you see? And then when it gets there to be 0, and continue increasing when it gets there to be 0. Now, but the acceleration is almost there. So what happened? We're going to look at the fact that the energy of a simple pendulum, when I consider this, so this is the pendulum itself. So I'm going to consider this as the horizontal level, then which is from here all the way to this place is going to be the height of this length or the length of the thread. So I'm going to call L. This is a fixed point because there is a hook or a support, just like you are seeing there. So what happened when this is released to one side as it's happening on the screen? We now say that it could go to a particular point here. Now, what have you noticed? And then maybe at this point too. What you notice is that it was at this level, but then at this point now, there is a height opened. It has opened a height. That means at this point, the height was 0. Height equal to 0 at this point. But you see, it keep on increasing at this point now. So it keep on increasing in height, and the height gets to this level now. The same thing happens, keep on increasing in height, and gets to this point. Then comes down, increase again. So at this point, the height is 0. What I mean is, I'm not talking about the length of the thread, because this is the thread. Or the string. This is the string. I'm not talking about the string or the rope. I'm talking about the from the beginning to the end. It's the same thing here too. It's the same thing here too, but then when it gets to this point, it slants, and then it's no longer as it is here. That is what we are saying. Now, we are saying that what is the energy of a simple pendulum? That means, what is the energy here? Potential energy, kinetic energy. At this point, potential energy, kinetic energy. At this point too, potential energy and kinetic energy. Now, if you realize that if height is 0, then kinetic energy is going to be 0 at this point. I mean, at this point A. Then there is point B, probably point C. Now, what happened to velocity? Velocity is going to be maximum here. I mean, kinetic energy is going to be maximum. So kinetic energy is going to have its full value at this stage. So when it gets to this place, the potential energy is going to be highest at this point, is going to be maximum. Because at this point, it has gained height because kinetic energy, pardon me, potential energy at this point is a function of height. So as the height is increasing, before it gets to this point, then potential energy is increasing. So when it gets to this point, it has gotten to its maximum potential energy. The same thing, when it keeps on increasing, when it gets to this point, it has got to its maximum potential energy. But what happens to kinetic energy? At here is 0, and kinetic energy at here is 0. Then potential energy at this place is also what? Maximum. So these are the 3 stages involved in this whole process. Now, remember that then, if we are also talking about, we now say that this particular body now is going to move in this direction because this is going to be the force pushing it this way. Or I'm going to call it the tangential velocity is also going to help in pushing it this way. Because if you're looking at this now on the screen, you realize that this V, like I said earlier, it will get to the, become 0. And that is why those arrows for the blue, which is velocity, is increasing and reducing, as the case may be. It is because kinetic energy is affected by the velocity of a body because it has to do with the movement of a body. And this is the energy of simple pendulum. But one more thing I want to say here is that according to the conservation of mechanical energy at any point is constant. That means mechanical energy at this point, mechanical energy at this point, and mechanical energy at this point. Now the question is, what is this mechanical energy? Mathematically, mechanical energy is equal to kinetic energy plus potential energy. So if potential energy is maximum here and 0 here, that means mechanical energy at this point is going to be only potential energy because kinetic energy here is 0. The same thing happens here. Mechanical energy at this point is going to be potential energy, mechanical energy here. So ME is going to be potential energy because kinetic energy is 0. But then at point A, mechanical energy is going to be kinetic energy because potential energy at this point is 0. So we say that at every point, total energy, which is called ET, which is how many textbooks call it, is equal to kinetic energy plus potential energy at every point as this body is moving from one point to the other. Now let me leave you with a little thing to think about. If we are only considering this point A, point B, and point C, what happens when we consider a point on this place? Let me call A prime, small a, and probably a point here, B. What would be the kinetic energy at this point, and what would be potential kinetic energy at this point? Now let me say this. At every point as this body is moving in this direction, kinetic energy plus potential energy is going to be equal to the mechanical energy. And that is the principle of conservation of mechanical energy. Okay, so we are looking at the period of a simple pendulum. For us to be able to consider this period, we have to look at the length and then acceleration due to gravity, because these are the two constraints or conditions we have to consider before talking about this period of a simple pendulum. But I want us to look at this, looking at a simple pendulum, which is this string and a bulb on it. Then we have the bulb on this particular, a full displacement, I mean from the origin, this is the equilibrium, And at this point, we say that it has reached its maximum, or the amplitude, which is the highest displacement from the equilibrium point. Now, we can also get to this point whereby it's also in the other direction, because it is a two-way thing, positive and negative. So if I consider this as the full length of the pendulum, which is the length, then I will also look at this point as the point it got to after opening this height in this direction, then with an angle, theta. This is also length, and this is also length. Now, we are going to consider the fact that there is a force that will pull this to the center, and that force, and then consider the fact that the acceleration in this point is going to be linear acceleration, but with the help of this angular speed that will still bring it back to the center because of the curve it is making. Now, what we are going to do is, from the beginning, from this part now, let me call it 0, to the end, we are looking at, from here, let's say point A to point B, I'm looking at x, which is the displacement. So if from A to B is the highest displacement, I can call it amplitude, but I'm looking at it as x, which is the displacement from the origin. Now, I'm looking at this force as minus mg sine theta. This minus mg sine theta is the force which is bringing it back to the center, and that is why we are giving it as a negative sign, because the body was taken to this part and then let go, the body brings it back to the center, so it's negative. Then that force, according to the Newton's second law of motion, this force is going to be equal to ma, yes, because of the acceleration here. Now, the acceleration in this case, let's cancel this, and this will cancel. Remember, like I said before, that there is an acceleration bringing it back. If I can take a little back to this place, you see that there is A on this red arrow. That A is always dragging it back, also helping the velocity there, and then bringing it back to center. That is why they say that simple harmonic motion is the up and down motion, so that the acceleration is directly proportional to the displacement and always coming back to the center of equilibrium. Now, if I cancel, then I have minus g sine theta is equal to A. And that A, acceleration, I'm giving it as this, because in terms of angular rotation, and this is angular velocity, which is as a result of the movement of rotation. So that means I will remove this acceleration and replace it with this. Then this minus cancels this minus. Then, but before that, remember that from here to here is x, then from here to here is also x. Remember. Then in this case, we are going to say that if this is angle 90, we are looking at this as a right angle triangle. And if I apply trigonometric ratios, I'm going to say that this with respect to this is going to be sine theta is going to be opposite multiplied by the hypotenuse. Remember, this L is not just, the L is from the beginning to the end. So this is the L, so it's not just that. Now, which is going to be x over L, because this is opposite and this is hypotenuse. And that is what this sine theta is. So what I'm going to do now is going to be, I will remove this sine theta and replace it with this. Even though they say that in one of the assumptions is that this angle, sine theta is going to be very, very equivalent to a very small angle, which is the theta. Yes, that the value has to be very small to the angle you are seeing there on the screen, which is the theta. So whichever way, we are going to say that G multiplied by x over L, which is equal to omega square x. Now remember, this x will cancel this x. So let me make myself a little space here. So I'm going to have that G over L is equal to omega square. If I take the square root of both sides, this will cancel this. I have that omega is equal to square root of G over L. Now, this is it. Now, let me also make a few more assumptions before we will be able to talk about the period of a simple pendulum. Let's go back. Yes, the period of a simple pendulum, this is where we are now. Now let's talk about the fact that this omega is given as 2 pi f. This is when we talk about 2 pi, we are talking about the circular motion that is in radian, the angle in radian, and this frequency. Therefore, if I do this, I'm going to say that omega is equal to 2 pi. Remember that frequency is equal to 1 over t. So I'm going to say times 1 over t. So omega is going to be 2 pi all over t. All right, if this is true and this is true, therefore we're going to say that if this is equal to this and this is equal to this, therefore this must be equal to this. So we say that 2 pi all over t is equal to square root of g over L. Now, whereby, what is L? L is the length of the thread, while g is acceleration due to gravity. Now, let us make it the subject formula. I am going to, let me break things up. I'm going to say that 2 pi over t is equal to square root of g up all over square root of L. So when I clear the fraction, I'm having t square root of g is equal to 2 pi square root of L. Therefore, t is equal to 2 pi square root of L divided by square root of g. Therefore, t is equal to 2 pi L over g. You see that? This is the period of a simple pendulum. Now, the period of a simple pendulum, whereby t is the period and the L is the length of the thread of the string holding the pendulum, and g is acceleration due to gravity. So this relation talks about the period of a simple pendulum. Now we have a problem here. We said that calculate the length of a simple pendulum that oscillates with a frequency of 0.4 hertz, take g as 10 meters per second, and that should be pi, 3.142. Okay, the length of a simple pendulum that oscillates with a frequency. Now, we know that t is equal to 2 pi L over g. Then we know that t is equal to 1 over f. We are now asked to find period. Therefore, I'm going to remove this. I'm going to say half over this is equal to 2 pi L over g. G is 10, so I'm putting 10 straight away. And f is 0.4, so this is 0.4. So I will remove this 2 pi r. So I'm going to multiply by 1 over 2 pi, 1 over 2 pi. So 2 pi will cancel 2 pi. I'm going to have 1 over 2 times 3.14, because pi is 3.14, times 0.4 is equal to square root of L over 10. So 0.2 times 3.142. So I'm having 1 over 2.514 is equal to L over 10. So what I'm going to do, I'm going to take square root of both sides. I'm going to square both sides, not square root. I'm going to square both sides. So I'll square here. This cancels this. I will have that 1 all over, so I have 2.514 squared. I will have 6.320 is equal to L over 10. So when I clear the fraction, I'm having that L is equal to 10 all over 6.320. So L is going to be 6.320. So L is 1.58 meters. So that is the length of this the simple pendulum that oscillates with this frequency. Now, we also have another one. We said that a simple pendulum, 0.64 meters long, has a period of 1.2 seconds. And another pendulum of 0.36 meter long in the same location. In the same location, we are looking at acceleration due to gravity. Okay, we have two different pendula. One, 2 pi. The first one is, the length is 0.64 all over 10. Okay, I'm using G because they didn't give me the G. And then there is another one. So T2 is 2 pi. The length is 0.36 all over G. Oh, we are given the T1. So T1 is given as 1.2 and T2 was given as okay. We are supposed to be given this second one. The period of the second one was supposed to be given. For us to find this in the same location. Oh, therefore, I'm looking for the T2. Yeah, we are looking for the T2. So in this case, I'm going to make G the subject formula here, and make G the subject formula here, and equate them because that is the only option I have. So I'm going to have 1.2 all squared is equal to 4 pi squared times 0.64 over G. Therefore, G is going to be 4 pi squared times 0.64 all over 1.2 all squared. This is the first one, the first location. The second location is going to be, G is going to be equal to 4 pi squared times 0.36 all over T square, that is T2 square. Now, this is the first location, and this is the second location. I'm going to say this first location equal to the second location. And that's going to be 4 pi squared times 0.64 all over 1.2 all squared is equal to 4 pi squared times 0.36 all over T squared 2. So this is cancelling this. Then, that's correct. So I will have 1.2 squared. I have 0.64 all over 1.44 equal to 0.36 all over T square. That is T2. So I will so I have 0.64 times T squared 2 is equal to 1.44 times 0.36. So I said that T is going to be 1.44 times 0.36 all divided by 0.64. So T2 is going to be 1.44 times 0.36 divided by 0.64. We have 0.81. So T is going to be, T2 is going to be square root of 0.81. We have 0.9 seconds. So it's going to be 0.9 seconds according to this question. Now we are going to energy of a spring. So when we talk about energy of a spring, we are talking about the energy stored in the spring that makes the spring to do work. Remember what spring can do. Spring can carry you. The weight you are measuring, your mass you are measuring is the spring that's carrying it. When you are buying things in the market, sometimes it is measured with using a scale. So that is the work the spring does. So what we are looking at, what is the energy of this spring? But before we look at that, we have to consider that every time we talk about energy in this concept, we are looking at the mechanical energy. So the energy of a spring is going to be that the average force, that is force divided by 2, times the displacement, that is times distance, S in this case. Now remember that this is a spring, and when we are talking about spring, you have to respect Hooke's law, because he is the one that says that the force applied is directly proportional to the extension. So in that case, we are going to give it to him, because there is always an extension, which is E. So we are going to say that this force is going to be, according to Hooke's law, we're going to say that KE, I'm using Y here because we are talking about distance from the equilibrium position. So, and then the extension is going to be here too. So I'm going to say that the work is going to be 1/2, instead of F, I'm going to say KY times displacement. In this case is also going to be this one. So you say that the work is going to be 1/2 KY squared. This is the work in a spring. This is the energy, the work or the energy stored in a spring. And remember that when we are talking about the total work done or the total energy of a spring. Now, let's talk about, this can be the work, it can also be the potential energy. Because when we are talking about the work, we are talking about the work done with respect to distance. So when the distance is an up vertical distance, we look at it as the height. And remember that kinetic energy is mgh. So for a spring, this is either the work or potential energy of the spring. Now, in terms of the total work done or total mechanical energy of a spring, we are going to say it's going to be kinetic energy plus the potential energy. Now, that means that we are going to have 1/2 K A square. Why am I using A? Because we are talking about the amplitude, which is the highest distance. The amplitude, which is the highest distance, which is more than this. Because that is the total energy, which is going to be, kinetic energy is the movement of the body, which is going to be half mv squared, plus the potential energy, which is half ky squared. So this is the mechanical energy or total energy of a spring as it is given. Now, let's move on to talk about the period. The period of a spring, we are still going to move on from, continue from where we stopped here. Looking at the period, we are looking at the time it takes to complete an oscillation for a spring. Now, I am going to find V. I'm going to find V here and see how we relate them. So in this case, I'm going to cancel this. Yeah, I'm going to cancel it because I know that this and this is going to give me 1. All right, let's do it this way. Let's continue with our process to avoid a mistake. Okay, so I'm going to have that 1/2 Ka squared is going to be equal to 1/2 bracket mv squared plus ky squared. You see that? So they will still cancel. This will cancel this. So have Ka squared is equal to mv squared plus ky squared. So k's will go one side. So I'm going to have K A squared minus Ky squared, which is equal to mv squared. So K is constant, is common. So I'm going to have K bracket A squared minus Y squared, which is equal to mv squared. So divide both sides by m. So this will cancel this. So I'm seeing that V is equal to K A squared Y squared all over m. Remember that when we talk about the velocity or the tangential velocity of a simple pendulum, we say that it is the same thing as this, omega. Yes. Whereby we can also say that, because at this point, this is when the amplitude is really talked about. But when we are talking about this, we are talking about there is a change in distance, which is not really the full distance. So what do? I am going to change this one to the one we already know, which is, we're going to say this is y squared So I'm going to do some comparison. But before then, I also want us to consider this. I want us to consider the fact that omega is 2 pi f. This won't help much. Then we also say that V is equal to a squared y minus y squared square and omega. So I'm going to compare these two. That's the best thing to do now. Compare them, let them cancel wherever need be. So I'm going to say that half k bracket a squared minus y squared all over m is equal to v. So this is v and this is v. So I'm going to have that is equal to k a squared minus y squared all over m. Then this one has omega here. All right. So if I take the square root of both sides to cancel this, I'm going to square both sides. So this is going to, this will cancel this and this will come here. I will have that k a squared minus y squared all over m. Now, I'm going to say that omega is going to be equal to square root of k over m and then a squared minus y squared. So in totality, we can say that omega is given as, square root of omega is given as k over m, whereby omega is going to be square root of k over m. Then the period of a pendulum is going to be given as 2 pi all over k over m. That is for a spring. Okay, we are looking at the period of a spring so we said that T 2 pi of this. Now let's look at a problem. Now we have this, we said that a mass attached to a light spiral spring is caused to perform simple harmonic motion of frequency this, where k is the force constant of a spring if mass is given as this and force constant is 30 Newton per meter and the maximum displacement of the mass from the equilibrium position is 0.015 meter. Calculate the maximum kinetic energy of the system. All right, the maximum kinetic energy of the system, like I said, is going to be half mv squared plus 1 over 2 ky squared. All right. However, all this can be is going to be ka squared. Half ka squared can be this, the value. Now let's look at how all this can be given. Now we are given the frequency, and remember something, that the frequency is equal to 1 over t. Now let's get started on this. So I'm going to be given as mass because I'm going to use this relation here. So t is given as 2 times pi is 3.14 times mass is given as 0.3 all over K is given as 30. Now, what I'm looking for is the kinetic energy of the system. So, in the kinetic energy, like I said, we have half. Kinetic energy of the system, like I said, is half mv squared. Now, we have maximum. Calculate the maximum kinetic energy. Sorry. So the maximum kinetic energy has to be with this over 2, then ky squared. All right. So the displacement from equilibrium position is 0.15. All right. So in this case now, A is 0.15. Now, okay, let me do it this way. Let's start from saying that maximum kinetic energy, the total energy of the system is going to be given as 1 over 2 Ka squared. Yes. So the total energy is going to be 1 over 2 times 30 times 0.15 all squared. And that is the total energy is going to be. This is 15 times 0.15 times 0.15. So we are having 0.3375 joules. All right. Now, then we also remember that this y was not given. And we also have to know that v is given as a squared minus y squared, square root of this times the omega. And I know that omega is 2 pi f. So, if we'll have this expression now given as the energy, then I'm going to say that this is going to be minus this is going to be my kinetic energy. Then if I have my period, okay, so I also have that omega is equal to 2 pi over t. Yeah, 2 pi over t. And that is going to give me, I will have that omega is going to be 2 times 3.14 all over period. Let me finish this to get my period. So I'm going to have 0.3 divided by 30, 0.01, square root of 0.01, 0.1. So I'm going to say that from here, I'm saying that T is going to be 2 times 3.14 times 0.1. So T is going to be equal to 2 times 3.14 times 0.1. So T is 0.628. So I'm going to have 0.628. So omega is going to be 2 times 3.14 divided by 0.628. So omega is 10 radian per second. And I'm going to apply that here. So I'm going to say that V is equal to, the amplitude is given to me as 0.015. So this is this or this omega. V is going to be 0.015 because they say is the maximum displacement times 10. V is going to be 0.15 meters per second. Now, kinetic energy is given as 1 over 2 mv squared. and V is already given to me. So kinetic energy is going to be half times the mass is 0.3 times V is 0.15 all squared. So kinetic energy is going to be 0.15 squared times 0.3 divided by 2. So I have 3.375 times 10 raised to the power minus 3 joules. Now, the tension of the spring, the tension in the spring, when we talk about the tension, we are talking about the force plus the weight. So in this case, the weight is going to be 3. Force is going to be 0.3 times 10 is going to be the force. That is going to be the force. The force, okay, let me find the force, because remember that this is a spring. So the force is going to be Ky. So the force constant is given as 30 times amplitude, 0.13. So F is going to be 30 times 0.015. Times 0.015. 0.45. Then if I now say that the tension is going to be 0.45 plus weight, which is 0.3 times 10, which is plus 3, that is going to be 0.3, sorry, let me put it this way. Weight is going to be mass times acceleration due to gravity, and weight is going to be mass is 0.3 times 10, and then the weight is going to be 3. So if I'm going to have this, like I said before, I said that the tension is weight plus the force. The two of them put hand together to give you the tension. So in this case, I'm going to have 3 here. So tension is going to be 3 plus this is going to be 3.45 Newton. Is going to be the tension in the spring. Thank you for being part of this class. Remember, before we go, we are going to take a few more exercises from Examguide app. Okay, we have this question on the board. We said that a body moves in simple harmonic motion between 2 points. Not really talking about simple. Let's take another one. A particle vibrates with a simple harmonic motion. If its acceleration in meters is 25 times its displacement in meters, find the period of the motion in terms of pi. Okay. We know that acceleration is given as this. Now, they said that if its acceleration is 25 times its displacement, that means acceleration is 25x times its displacement. That is it. Therefore, I'm going to replace this acceleration as 25x equal to omega square x. So x will cancel x. We have that omega square is going to be 25. Then remember that omega is something as 2 pi f, or omega is something as 2 pi over t. And I'm looking for the period in terms of pi. So what I'm going to do is I will replace this with 2 pi over t. So I'm going to say 2 pi over t all squared is equal to 25. So I'm going to take square root of both sides. So I will have that 2 pi over t, this will cancel this, which is going to be equal to 5. If I cross this, I will have that All right, something here. So this is 5t equal to 2 pi divided by 5. T is 2 over 5 pi. T is going to be 2 divided by 5, 0.4. So this is 0.4 pi seconds, and that is option D. Thank you for participating in today's class. You can practice more questions using the Examguide app. The app scores and gives a detailed explanation of all the questions at the end of your practice test. You can learn a particular topic of interest with different modes like study mode, mock mode, and practice mode. It also has other features that makes learning fun. It is a must-have for all serious students. Download from www.examguide.com if you don't have it yet. See you in the next class. Don't forget to subscribe to our channel, hit the notification bell, and share the video to people that will benefit from it. Bye.